otherwise, I would continue, and that now, of course, makes sense. We'll look at the directly now at the spectral element method, which is okay. Can you see this? Yes. Can I get feedback? Okay. So let's directly look at the spectral element method, and probably I can. It's exactly the same derivation, which is why I can probably be quite fast. And I say here the key difference is the choice of the basis functions. A, B, because we allow the material parameters to vary inside the elements, we have to do something more intelligent about the calculations of the integral for mass and stiffness matrix. Those are the key differences. Otherwise, the mathematical ansatz is the same. Okay, so again, in a nutshell, I've said this before. Here's our snapshot again. It's a real snapshot. And now we go into an element. And there's already a lot of information in this picture. And sometimes it helps to hear it twice. So this is one element that you see at the top. And it's defined between -1 and 1. I mentioned this before. The reason is that Lagrange polynomials are defined between -1 and 1. Like Chebyshev polynomials as well. Now, again, this is not made up here. This is part of the wave field here. You know, this is the value at the left boundary, and this is the value at the right boundary. The first thing that is important is we now have there's a term collocation points. We now not only have let's say 2 degrees of freedom per element, we have more. In this case, we have 5, and 5 minus 1 is 4, and this is a 4th order Lagrange polynomial. And the basis functions, basically for each of those polynomials, you can see here. So again, these that's very similar to what we had actually in the Fourier method. Here, our basis functions, again, this is 1 here and 0 at all other collocation points. You will see this later. So the fine lines are they are basically the Lagrange polynomials that correspond, or the basis functions that correspond to each of those individual collocation points. You can also call them cardinal functions. Okay, and you see the equation here. Again, the weights are called ui because the basis functions have the value 1 at each of these collocation points, and li by xi, because this is actually wrong. This is wrong. This is in this figure. This should not be x. This should be xi. That's a mistake, and that probably even is a mistake in the book. I have to check that. That should be xi. Okay. So again, I put here in boldface the mass matrix will be diagonal because of a specific choice of integration scheme. And that means the whole problem becomes an explicit extrapolation scheme, just like a finite difference method. And that's very efficiently parallelized. And you could say it's the method of choice at the moment. We have only one or not many, Axis and 3D and Spectrum are more or less the only, and Salvus now, the only community codes for global wave propagation. However, meshing is required. Computational meshing. Okay, now let's go step by step again. We've seen this before. We can go very fast. Let's look at the one-dimensional equation, how we do this with spectral elements. Weak form of the equation, we've seen this before, nothing is different, okay? I can be quick on this. Again, we have, we do integration by parts. We use the boundary condition that the partial derivatives are 0 at the edges. Actually, one should add the mu here to be consistent, and then we replace our continuous u by an approximation of u bar sum over some basis functions. Okay, so we've just seen this, so I think that should be clear. Now the system of equations that is being generated, again, we've seen this before. We now go to the element level. Here is containing these matrices here, exactly the same as in the linear case. Nothing is different. The only thing that is now different is the following. We keep the density and the shear modulus here, the elastic properties, inside the integral. That has dramatic consequences in the sense that while these phi j's, phi I are where, you know, whatever choice are analytically known, we impose them. We can also calculate analytically, basically, these matrices. If you have a general distribution of rho as a function of x and u as a function of x, this is no longer possible. You have to do numerical integration. And that's one additional aspect of the spectral element method. And we'll get to that in a minute. But otherwise, so far, it is basically the same. So while we had these linear basis functions in the finite element method, phi I, we now replace these phi I by Lagrange polynomials that have this, you know, product type of formula that generate them. And if I see an equation like this, I have no idea what these functions look like. But it's actually relatively easy to code that and plot them. They are defined between -1 and 1. And so for an nth order polynomial, you are going from 1 to n plus 1. So what did I look like? Here's some examples. So actually, n equals 1 is a n equals 1 would be the linear case again. So you would have only one point at the edges and another point at the edges. It's actually, it would be possible. I think my code starts at n equals 2, but it would be possible to start at n equals 1. So you would have the linear, you would recover the linear finite element case. So again, you see these for n equals 2, you have 3 collocation points. So the order n will be important. That's something I want you to change when you play around with these codes. N equals 2 would be here the order. Then you have n plus 1 collocation points. Okay. Now the first basis function is 1 here and 0 here. You can see that. Second one, 1 here, 0 here, and so forth. Okay. And here's the same for n equals 6. Now, something very important and relevant is you can already see the collocation points at which, you know, these are the, in Germany, Stützpunkte. It's where you know your solution, where you have the displacement fields. They are not evenly spaced. Okay. if we had more time, when I introduced the pseudospectrum method, I would have shown you also the Chebyshev pseudospectrum method, where this is actually also the case with Chebyshev polynomials. So you can see you can imagine if the order increases, then the difference between the distance between these points and the points close to the boundary is actually increasing. And that's shown in this graph here. So these are the collocation points, for the Lagrange polynomials as a function of order. So we start here at order 2. So order 2, quadratic function, you have 3 points. And actually, in this case, you have an evenly spaced points. As soon as you go to n equals 3, you see that the central distance here is larger than this. And you can also see that the ratio between the smallest and the largest is increasing, actually linearly. Now, a very important message here. Even though the spectral element method is allowing you to go to arbitrary order, that's a really cool thing. Capital N, you can change it in your code. You can go, you can drive it up to 10, 20. Maybe I can ask the question, do you see in our time-dependent problem, do you see a problem go to, you could think, well, I'm getting more and more accurate in space if I increase the order. And I'm asking the question to you, why do you think people actually stop at order 4? There is no one in the world, almost no one, who uses a higher order than 4. So this would be just 2, 3, 4. What's the reason? Why do people not go to higher orders with spectral element simulations? What could be the reason?
Probably the
have
stability.
An idea? Exactly.
Stability things, because
exactly
for higher orders it may need lower CFL number than.
Exactly. So the higher the order, the smaller is your smallest increment, call it dx. And that, of course, then dramatically decreases the time step. Okay, so that's the reason. That's why it is, it's a method that allows higher orders, but in effect, one usually is restricted to 4th order for practical reasons. Okay, good. So we continue. We now use these Lagrange polynomials. You can also, by the way, use Chebyshev polynomials. Something we could discuss later if you're interested. But then you will not get a diagonal mass matrix. So here's an example of interpolation with Lagrange polynomials. That's also something that's fun and you can do with some of the Jupyter notebooks. This is like, interpolating with cosine and sine functions, but of course you are doing basically limited area interpolations. That's the advantage of Lagrange or Chebyshev polynomials, is the assumption of periodicity that you have in sine and cosine functions is not required. Okay, that's why this is so powerful. So the system of equations, again, exactly the same, can be written like this in the spectral element notation. It's only that the mass and the stiffness matrices are now calculated based on this description using Lagrange polynomials. In terms of matrices and the way they look like is it's in pictorial forms like this. And again, the most important part is the mass matrix is diagonal. So it has now the same form as actually a finite difference formulation in those matrix vector way. And again, this is not just this is an actual simulation. These are these pictures, these values are from an actual simulation, and you can actually guess here that there are 4 elements. Okay, you can see that. And there's a force vector here, and here's the acceleration and so forth. And again, the K is banded. The stiffness matrix in this case would be banded. For the time extrapolation, same as in the linear case, we use this mapping for u present and u old, and then you have exactly the same kind of algorithm like in the linear case as a solution scheme. Okay, now there's a few additional things now that are relevant. So these mass and stiffness matrices have the same form. You have to replace here phi by Lj. But the point with this slide is, again, coming back now, rho and u are inside the integrals. So we have to do something about that. And here comes the trick. We are using the so-called Gauss-Lobato Legendre integration scheme. So this is now something very general. What do you do when you know a function? You want to integrate a function from -1 to 1, an arbitrary function f of x. What you do is you're replacing the function. You do an interpolation. You're replacing the function by a polynomial, and of course we replace it by a Lagrange polynomial, and then the integral is actually replaced by a sum over, a weighted sum over the functional values at collocation points I, and these are the same. It's the most important part. The same collocation points as the Legendre collocation point. These are called the Gauss-Lobato Legendre points. So the Pn of x. So from here, this function approximation is then actually simply an interpolation of the function using Legendre polynomial, something like we've just seen before. So we can already do this. And actually the weights, they're also related to the Legendre polynomials, but these weights are also, you can find them in tables. So the message of this, we have to do numerical integration, which we did not do in the linear finite element case. B, we assume that, let's say, the fields and also the, let's say, density and mu values are known at the collocation points. That's not a problem. And that's actually what we want. We want to change the values of mu and density at these collocation points. And C, we use the same collocation points, and that's different. Classically, the Gauss integration scheme does not use values at the boundaries, but the Gauss-Lobato Legendre integration scheme uses points at the boundary and the same points as for Legendre interpolation. And because of that, and because of the orthogonality of the Legendre functions, you then get this mass matrix that's diagonal. We can skip this one here. So now that we know that the mass matrix is diagonal, you can write down the global solution scheme. Again, these matrices in reality would be huge. We can do this with our toy problems in exactly that way. In practice, if you look at the spectrum code, it's certainly not done like that. But here, to explain the algorithm, we can do it like this. So in principle, to wrap it up, in such a spectral element code, you need to initialize the space-time domain. You have to impose the polynomial order, usually not more than 4. You decide about the source location, source time function, and the Earth model. Then what you need is the integration weights, the collocation points, and the Jacobian. That is, if you change the element size, you need to. The Jacobian is a coordinate transform into each element. That all this allows you to calculate the elemental mass stiffness matrix, and you have to then put all these together. We didn't talk about this global matrix assembly. Put it all together to have this linear system of equations that you then solve in the time extrapolation. And in the end, here you see that code part here looks exactly the same as for the finite element method, and you should check this out in the code. So it's, again, the difference is M is diagonal, and all the elements now have more than 2 points. They have whatever you want, n+1 collocation points, where n is the order of the scheme. And one of the beautiful things about a description like this is the following. Think of a one-dimensional velocity model here given up here. So you have 2,500 plus minus whatever, 10%. And let's say you inject a source here and you let the solution propagate in both directions, okay? And so here you see the solution with n equals 2. You know, a lot of dispersion, there's a lot of problems. And then you just increase the solution to n equals 4. And suddenly, I would say, as an experienced simulator, I would say, oh, that looks like a healthy solution. To be on the safe side, let's say you could go to n equals 6, and if the solution doesn't change, you could say, I'm converged. That's the correct solution. And here's another very important message. In general, we do not have analytical solutions to check whether a complicated model like this one is correctly modeled. One way to do this, assuming that you have, a correct code and you have no bugs and errors, you can increase the order of your scheme and see at some point whether the solution changes no longer. And then you would assume you have found the right answer. That's a convergence test that's very frequently done. And that's what, if you want to be on the safe side with a complicated simulation, that's what you should do. That's expensive, but if you want to be sure you've modeled things correctly, that's what you have to do. Okay, and final statements. The many applications, regional global seismology is probably, at least in seismology, not so much in exploration. Spectral elements is the method of choice whenever surface waves are involved. Exploration doesn't need surface waves. There's a very clever combination with a cubed sphere for global applications, solid structure interactions. In principle, it works with hexahedral and tetrahedral meshes, but if you use tetrahedral meshes, you no longer have a symmetric mass matrix. And I think also the thing, it was taken out of Salvus. They started with having both tets and hexes, but at the moment I think they only have hexes. Okay, so that's these questions we can discuss. What are some major points? Speak for finite spectral elements. Maybe think about this. Why are spectral element methods so efficient? Parallel computers, mass matrix. Why do you think the spectral element is called spectral? I give you the answer. It's because of the spectral convergence of the basis functions. It's kind of the how quickly these you converge if you interpolate a function. So that would be the. Let me stop here for a moment, and we need to take a deep breath. I think that was a lot. So. You know, come up with questions maybe now on spectral elements, because I think this is the solver that probably most of you will use at some point. Any questions at this point?
I would have a question.
Yeah.
So, when using a spectral element solver, it's like, without maybe knowing the exact algorithm behind. So for example, with solvers, what are, in your opinion, kind of the biggest pitfalls I should take care of? Like the major things to look at, the obvious mistakes to not make, kind of.
What should I say here? The most important thing is that to get, you know, that's independent of spectrum, is to avoid numerical dispersion, to make sure that you are in the healthy domain of the numerical accuracy. There is no, to my understanding, there's no check. Nobody will complain if you, let's say, sample the wave field with not enough grid points per wavelength. Nobody will. There may be a warning, but there's also something that is expressed in many papers. People say, you know, when they introduce these methods, they say, well, my method works with 8 grid points per wavelength. But that's a totally nonsense statement, because of course it depends on how many wavelengths do you propagate, because of course errors accumulate. So, you know, I don't know your problem. If you suddenly say, okay, I want to simulate, you know, along a bar, lots and lots and lots of, you know, a very, very long time, then there are problems. And I think the only way to check whether it's accurate is by doing such a convergence test, or benchmark, if it's possible, benchmark with known solutions. It's something we should talk about later. Maybe there are online capabilities to check with something like LOH, layer over half space. So there are analytical or quasi-analytical solutions to compare with. So I think that's the you know, these codes are very stable, but I think that's the main trap. Other things, problems are, you know, what is the degree of heterogeneity of your models? If you know, have a very small low velocity layer somewhere, are you sure that this is properly covered by the parameters of your scheme? Again, this can be checked with you know, with a convergence test. So these are the main things. Maybe there are some other people have also experience with spectrum and found some traps. We can also talk about this later.
Thanks anyway. Thanks a lot.
Okay. Any other questions at the moment? Okay, so I suggest I go another 10 minutes and then we have a break. Is that okay? So let me share the screen again. So we're leaving an important block now, okay? We can close our minds to some extent and open up to something entirely different. So this was the finite element spectral element part, weak form, and now we sort of enter another quite different world in terms of how things work. Now let me find again. And we start with the finite volume method. The finite volume method was, my understanding, it was developed in Los Alamos, you know, where the atomic bomb was built many years ago, and it was on some neutron diffusion problem or something. It's let me see say in a nutshell again. It is, here is our snapshot, and I call this here Q. This is a property Q that can be displacement, that can be anything, can be pressure. And now the difference is that we have volumes instead of elements. The reason why it's called volume, they can actually have arbitrary shape. That's a cool thing. They can basically have arbitrary shape. So here in one dimension it's trivial. And what you do is, this is our field. So this is again this Gaussian shape. This is our displacement field. And what you do is you basically replace the field by the average value inside your volume cell. Okay, so you can see this horizontal bar is the average of this dashed curve. This is the average of this line here. This is the average of this line here. And if you extrapolate the system in time, let's say you know that there is a flux into the right direction. The flux would be the velocity of a wave that's known. You can estimate how much of this energy or displacement is basically in the next time step flowing into this next volume. Okay, so that's in a very simple terms what the finite volume method stands for. It has extreme geometrical flexibility, which is very important for example, something like shock waves. It's an entirely local formulation. It's cell-based, so that's good for parallelization. And it's fair to say it's hardly used in seismology, even though I think it is a very interesting method. Okay, now bear with me for a few minutes carefully. This is a very interesting derivation here. It's let's say we have this volume here between XL, XR, left, right. These are left, right boundaries, and A is a flux. A is a, A can also be, let's say, a wave velocity going in one direction. And Q is the field inside. Now Q can be, it can be anything. It can be mass, it can be a displacement, it can be energy. Now, let's assume it is mass. What we now do here is actually we're applying the conservation of mass. Can also be energy, but we're applying conservation law. So the total mass inside this is of course the integral from left to right over space. Okay. Now if anything changes, in a certain time, if anything changes in this volume, so if that the mass changes inside or the energy changes, it has to be related to a flux at the boundaries. And this flux is the flux 1 and flux 2. And these are rates, these are rates is something per second. Let's just accept that, okay? Now, if we assume, let's say, a transport velocity a transport, again, this can be the velocity of a wave, but it can be, think of a river, that's advecting something that's inside the river. That's an advection velocity. Now, let's assume that flux is A times Q. So this would be the flux in and out of a boundary. Then let's write it in general. This is a function of the field itself. Then you can just write it like this. This is a function of Q at x1 and a function of Q at x2. Defined at these boundaries. And that's called the integral form of a hyperbolic conservation law for the volume that we're looking at. And now comes an interesting trick. This looks like this looks like an antiderivative, right? This is something evaluated at the left boundary and at the right boundary, and you can basically rewrite this as an integral. So if you take the derivative, the space derivative of this f, and turn an integration, then if you solve this integral, you end up with this term here. Okay, so you can write it like this. I'm sorry, you can write it like this. Time derivative of the change of mass is related to this integral, and suddenly we have another integral from x1 to x2. So we can write everything below this one integral form, and then if if this has to be 0, we can also remove the integral. And what you obtain is the famous transport equation. So we just derived the transport equation, which is actually also, if you want, the most fundamental form of the wave equation. That's something I learned from a book on finite volumes. Is we always assume that the second order wave equation is the most important wave equation, and but you can actually derive the acoustic wave equation from this advection equation. So that's the more fundamental wave equation, and I accept that point. And we just derived it just by simply assuming the conservation of mass. Okay, so now how do we proceed now to solve this equation? And what we do is we first of all say we replace the field itself by the average here, QIN. This is the same graph as we've seen before. That's the average value in one element. I think that's clear. And again, what we need is a flux term. A flux term is the integral over time now from t to t plus n of the flux across a certain boundary. That looks complicated, but if you know A, it's actually trivial. It's just basically you multiply the flux with the time, and then you have these values at the left and the right boundaries. And if you do that, you actually get from from this form to this discrete time scheme, qin plus 1 qin minus dt by dx, and the difference of this flux. So this is basically the solution of the advection equation based on the finite volume approach. You probably see already that this is in principle nothing else but a finite difference approximation. And that's, again, is one of the beauty of all these different methods. In their basic form, in their linear form, they are more or less exactly the same, even though mathematically or conceptually you take a very different ansatz. And so this is basically already it, what I want to say about the finite volume method, and now we're going to make a break in a second. I just want to highlight again that this method works in principle on arbitrary shape geometries or volumes. So, for example, you can use Voronoi cells. We actually coded a wave propagation solution based on Voronoi cells. And something that is important, that it come later if we talk about the DG method, is the so-called Riemann problem. What is the Riemann problem? It is the problem. Look at the bottom. The question is, I have volumes with, let's say, density or values in my cells, and the question is, if I have advection to the right, how much of this, how much is actually flowing from the left cell to the right cell? Okay, so what's the propagation of this discontinuity? Okay, so that's what's illustrated here. You know, we move from here to there, and basically that discontinuity is shifted. And that's called the Riemann problem. And the Riemann problem is the basis for the solution for, you know, the elastic case and these things when we talk about the discontinuous Galerkin method. So just remember that named Riemann problem that is connected to fluxes in finite volume and discontinuous Galerkin methods. So just to wrap this up, you can see here this on the left actually is from Martin Käser, my first master student or diploma student when I arrived in Munich a long time ago. And we used these triangular meshes to solve the wave propagation problem with finite volume. So it works, but it just requires an awful large number of grid points per wavelength, which is why it was not just not efficient. We never continued that. But in the end, these ideas eventually led to the introduction of the discontinuous Galerkin method for the wave propagation problem. So I think I'll leave it at that, and I suggest we'll make a break, half an hour, let's say until 11, and then we'll tackle the last one of the methods. Any questions? It's a lot of material. Yes?
Yeah, I may have just a question that's pretty vague, but so most of those methods actually, I mean, the end result is usually displacement, if I'm not mistaken.
Yeah.
And I mean, historically, that's probably because that's what we've always been able to measure pretty easily. But I mean, part of the SPIN project is also exploiting new sensors and new quantities that we can directly measure. So do you think there might be new numerical methods we haven't really seen in the past that could, like, I don't know, compute directly rotation fields or things like that?
Yeah, it's a good question. The answer is no. We don't need new methods. If we simulate displacements, we usually, depending on the method, in some of the methods like the finite difference method, we always also calculate strain or the gradient, and we could extract that easily. With it's also possible with the spectral element methods. You can, once we are describing the field with the Legendre polynomials, it's very easy to then actually calculate the derivative of these functions inside the code. So the answer is no. It's quite easy to extract strain and rotation. It's a couple of lines of code. So the answer is no. I don't think we need new solvers.
Okay, thanks.
Any other questions? Okay, if not, then let's take a break and we meet again 11:05. Okay?
Oh, Heiner.
Yes.
I just thought of a question. Does the fact that the finite volume method is based more on conservation laws rather than the equations of motion make it easier in that formulation to handle things like self-gravitation and stuff, global, like where you can just write down the potential energy of the system and make sure that it's conserved?
I would guess so, but it's one of the things is that you can fulfill really an energy conservation, and so I don't know specifically, but that's the beauty about this method is you can, it's more physical, it's closer to physics. The other techniques are basically purely mathematical, but here you basically coming with a physical concept of a conservation law. Whether that works for gravitation, I don't know. I'd have to check. Are you still there?
Yeah. Yeah, I was wondering if there could be some other schemes based on, like somehow numerically solving from the Lagrangian or something like that, rather than like Newton's equations. But that's a very ill-conceived thought on my behalf. I haven't really thought about it properly.
So are you in the Tyus group or?
Yeah, I've just started a postdoc with Taya, and sort of the goal of the main part of my postdoc is trying to develop emulators for the seismic wave equation using deep neural networks.
Oh, okay.
Try to solve them approximately more quickly if you want to repeat
cool
equations.
Yeah, cool project. Yeah. Okay, so maybe let's get some coffee. Okay, So final leg, at least in terms of the 6 numerical methods that we will have learned or seen maybe for the first time. The Discontinuous Galerkin Method. Funny name. It first of all, let's think a little bit about the wording here. It's a Galerkin method. It's basically a finite element method, just like what we've seen before. And the key word is the discontinuous. We've seen in the finite element spectral element method that the fields were actually touching or continuous at the element boundary, and this will no longer be the case. Now we'll have fields that are discontinuous at the element boundary, and that's one of the key aspects of this method. So again, let's basically look at this in a nutshell. Again, we have an actual wave field modeled, simulated with the Discontinuous Galerkin method. And it's a finite element method. So again, we have elements. Inside these elements, and now is we will have the same, and at least in this implementation, we will have the same basis functions as in the spectral element method. So something I'd like to say here, the Discontinuous Galerkin method is a little bit the result of taking the best of everything. The best of spectral element methods is the Lagrange interpolation. So we use the same Lagrange interpolation functions inside the element. We take the best of finite volume method because we make actually use of the flux, exactly the same flux terms that were introduced in the finite volume method. And for the time extrapolation, we basically can make use of the same finite difference type of extrapolation. So that's an interesting aspect, throwing all this together, coming up with a method that has been actually very popular in other fields, also of engineering, in particular in like aeroacoustics, and applied to a problem in seismology. And I should note, it has led to maybe at the moment the most successful code for dynamic rupture propagation. And you can maybe guess partly why. Rupture is something that happens on a boundary where we implicitly then have actually discontinuous behavior. It's from the beginning, we thought that's a method that lends itself to problems of rupture propagation. So, and the key aspect here is you can see it, it's my cursor, at the element boundaries, you basically have now a left value and a right value, which actually increases the number of degrees of freedom that you have to solve for. Okay, that's a disadvantage. So another aspect is this approach is an entirely local formulation. You're always sitting inside an element and you just look to the next neighbor and so ask, what's the flux coming in here? What's the flux coming in there? So it's a very local scheme. And there's quite a lot of work, a lot of, let's say, floating point operations to be done per element. And that's something that, computational scientists love. Problems with not much communication and a lot of work inside elements. And that's another reason why this algorithm was actually taken up in a long collaboration, goes back almost 15 years now here in Munich. And it has been the most efficient production code on our local supercomputer with a reaching about 50% of the peak, the peak flop rate basically on that machine. So very efficient parallelization is possible. Okay, now let's have a look at this. As mentioned a couple of times, we are solving the first order wave equation here in its coupled form. So that's a hyperbolic wave equation. And in matrix vector form, we write it like this. So the first derivative of Q, which is a vector in V and sigma, plus matrix A and the space derivative of the solution vector U and V. Now let's see that whether I don't have the vector A, the matrix A. This is just another way of writing this equation with the appropriate definitions for Q and A. Very simple, okay? But what is amazing, and you can see this, mathematically, we brought it back to the simple advection equation that we derived when we talked about the finite volume method. And that's the beauty of this. You can bring it back to this, mathematically very simple form. Even though if you look at the early papers, then these matrices Q and A, they become pretty well, Q not. Q is just simply three displacements and 3 velocities and 6 stresses, but the matrix A becomes already quite involved. Okay, but so it can be treated very easily. That's why when we introduce here the discontinuous Galerkin method, we actually start developing the solution for the simple advection scheme, and that can be then generalized to more complicated situations. So this is, we're going back to the simple scalar 1D advection equation, and so just in terms of notation, dk would be the domain for each element. This is the number of elements. We have n elements. X is going to the right. So this is now important because there will be a left and right boundary for each element that we denote as xlk and xrk. Again, here something very easy to do is the so-called H adaptivity. I mentioned this word already. That's basically changing the mesh size, changing the element size for in this case is really straightforward. And forgive me, I'll go back once more to this and I'm always, because it's important, I'm writing down another term. And you see, if you change, we just learned H adaptivity. And there is something else. Let's do it with a red. So there's P adaptivity. P adaptivity. Okay, now H adaptivity is clear. It's the size of the element that can be adapted. For example, in a low velocity region, you have smaller wavelengths, so you would like to have a smaller mesh width. That's obvious. Now, the P adaptivity is connected to the where's my mouse? Is connected to basically inside each element here, you have a polynomial of order p. So that's the p stands for the polynomial order. Now, something that's actually extremely difficult or impossible to do with spectral elements, to change the order of the scheme locally. Imagine, well, you have a global model and you would say, well, in the outer core, I only need order 2, and in the mantle, I want order 4. That's very difficult to implement. In the discontinuous Galerkin method, that's trivial. It's not a problem for reasons we may not get into now. But that's the P adaptivity. And that's actually a very powerful combination of tools, H and P adaptivity in an algorithm. Because, for example, I'll show a mesh later. On a volcano, if you model a volcano, you may, towards the edges, you say, oh, I want to use very large elements. And I use, let's say, very large elements with a high polynomial order because I don't have geometric complexity. And at the volcano itself, I have a lot of topography, so I want small elements, and then I would maybe need a lower order. So in terms of polynomial order. So there's a lot of flexibility. So these two expressions are important. Okay, so just a little bit of you know, we now have, if we formulate the problem like this, we have elements, and in each element, like in the first element here, we not only have 2 points like at the edges, but we have a vector of points, and that's expressed in this way. So we have kind of a different shape of the unknown vector is here, is no longer a vector of unknowns along one line, but we have a matrix with basically polynomial coefficients for each element. Okay, you could also, in principle, put this into a vector, but you have to be sure that you know this is the value at the edge of the first element, and this is the value at the beginning of the second element, and they are different. Remember again, in the spectral element method, they were the same. Here they are different, and so the coordinates of your of this unknown vector of unknowns would be here x1. This is upper index 1 is the element, and the lower index 2 would be the collocation points. This would also Lagrange collocation points, Gauss, Lobato, Legendre points in element 1, 2, and 3. Okay, so as you can see, that also increases, as I mentioned before, the number of degrees of freedom using this kind of method. The rest is very similar. Like this is now a weak formulation. So you have the scalar advection equation. We'll multiply it with a test function phi j, which will be Lagrange polynomials. So that's the same here. And for element k, we obtain, now this is you know, again on an elemental scale, we obtain this equation here. And what is different now is we have this antiderivative here. You can see this. This is the this is now the key difference to the derivation of the finite element method. This is not going to be scrapped away because of a free surface boundary condition. No, this here is the flux actually at the element boundaries. You can see this is evaluated to the right and to the left. And that's the fundamental difference in this Galerkin type of derivation. And I will not go into much more details about that. So one of the key tasks in this Discontinuous Galerkin scheme is basically, you know, what are the values here at the boundaries, because they are discontinuous. And this is the Riemann problem. You know, the Riemann problem is the question, if you have a discontinuity here, how does it propagate under certain, you know, conditions? And the condition is, of course, for example, the wave equation. So this is the same as we had before, and in higher dimensions, this is an evaluation basically at a surface. So in one dimension, it's just the left and right points. And in higher dimensions, in 2D, it's the surface of your element. or in 3 dimensions, it's the surface of the volume. And that involves, important here, the boldface n involves a surface normal at the edges. Well, you know, which is like -1 and +1, depending on which direction you go. And you just have to be careful if one formulates this about these directional issues of the normal vector. And then you develop so-called flux matrices, which is, you know, think about the basis functions inside an element. So these have the same, this flux vector has the same size as the you know, the polynomial representation of your field inside the elements, and the first value and the last value are non-zero, and they correspond to the fluxes in and out of the cell. And as you can see here, they simply multiply. This is the AQ. We've seen this in the finite volume method. It's just the flux term A times the advection velocity times the field itself, multiplying the basis function here, the Lagrangian basis function, and that is, but that's simply 1. So these are the flux matrices that, or flux vectors that you have to use at the element boundaries. So yeah, let's leave it at that for the moment. So otherwise, we end up with a matrix notation with involving a mass matrix and a stiffness matrix. All this is at an elemental level, and that equates the flux vector, which, you know, has only non-zero values at the edges. And so the extrapolation scheme then is, we've seen this in the finite volume method, also simply like this, and can be written down in this way using basically an Euler method that can be improved using an Runge-Kutta type high order extrapolation schemes. But in principle also the algorithm is written, you can check it out exactly in this way. So for the elastic case, that becomes a little more lengthy and involved, but in principle that is the scheme. So I think that's, yeah, here's an example of the code. It's basically a Python translation of this line here. Okay, you can see Q is a matrix now for each element, so that's a different. We have never seen it like this before. We have a sum over all elements. We have somehow we have to pre-calculate the flux at each time step, and then we can initialize or update the field Q in each element. This is the colon. That's an implicit loop in each element. Again, by simply having dt times the inverse of the mass matrix at each point times the stiffness matrix multiplying the vector of unknowns Q. So again, can be written in very simple terms. The ... involves, of course, all the initialization of the mass matrix, the stiffness matrix, and the flux terms. So this is again a pictorial representation of the matrix structures for on the elemental level. You have a square diagonal mass matrix. This is the velocity or the time derivative of the solution field. Matrix K, matrix Q, and the flux matrices, flux vector that has only elements at the boundaries. Here, for an example, order 3, meaning 4 collocation points. And again, this is one of the key advantages of this method. It's entirely local. All the calculations have to can be done on a local level. Of course, to calculate the fluxes, yes, you have to know things that happen at the adjacent in the adjacent element. So here's an example with 200 elements. I guess that's the example that is in the Jupyter notebooks. I invite you to play around with the Courant criterion. Remember, this was like 1 in the finite difference case. One of the disadvantages of the discontinuous Galerkin method is it turns out the Courant criterion is less favorite, so you have to have a smaller Courant criterion. And it's interesting to play around with that numerically. You just change it and see when the solution blows up, and gives you an idea where this is in comparison, for example, to the finite difference method. And here are some examples. A comparison now of finite volume schemes and discontinuous Galerkin schemes. Now, it is interesting, and we've not talked about this. So what you see here is basically you give an initial condition and you propagate it to the right. So this is a superposition of many time steps. Okay, so don't get this wrong. We start basically with an initial condition to the left and 0 everywhere else, and then we propagate to the right, and we just take the next time step here so that we can compare the accuracy of the solution. The analytical solution is the dashed line, and the numerical solution is the fine black line. Okay. Now, something that's very well known is that the classic upwind first order scheme is very diffusive, and you see that you're actually losing the solution quite early. That doesn't work. So a substantial improvement if you use the so-called Lax-Venthrov scheme, where you develop a small time shift, which is why the misfit still is pretty high, but at least the solution in terms of waveform is much more stable. And with the DG method, with the Upflix term Euler, so that's the same upwind scheme here, that's unstable. You can see that the solution explodes. And but then with the so-called predictor corrector method, that's a Runge-Kutta type of time extrapolation scheme, suddenly the solution becomes really very accurate. So then you're playing out the full power of that scheme, so it's very accurate. So here, that's something we have not discussed. The time extrapolation scheme plays an important role, and one cannot stick to the simplest possible finite difference extrapolation scheme as was possible in the finite difference scheme. Okay, so I can already wrap up here. So the DG method is based on these calculation of these fluxes that it can be complicated, but once this is implemented, the beauty of it works on. So this is a picture of a mesh of the Matterhorn, a tetrahedral mesh of the Matterhorn. And obviously, this is a method that is very well capable when you have strong, complex geometries in terms of surface boundaries, topography, or internal boundaries like complicated meshes. And that's what's currently really a hot topic in research is dynamic rupture. And Alice Gabriel's group, who will be here later today, this is their their domain of research with recent several papers in Nature Geosciences. This is really a hot research frontier at the moment. So to wrap up here, there are applications here. This the bottom I mentioned. This is Merapi volcano. This is the picture of what actually was a Gordon Bell finalist in 2015. It's already 7 years ago, winning awards. So in particular for shaking hazard earthquake physics, tetrahedral meshes, one has to say the method is expensive. It's computationally expensive. It may be efficient, but it's very expensive when you use TETs because you have more unknowns compared to hexahedral meshes. And it's but if you have complexity, it's the method of choice, for example, for dynamic rupture problems. There are new approaches. There was the ExaHype project. If you want to check it out, ExaHype, that has just been finished. And we'll hear more about Seisol later this afternoon. Okay, so that wraps up the DG method. So not continuous at the element boundaries. There are no large global system matrix needs to be inverted. You need a flux scheme. It's a local algorithm. And here you can actually, you can go to higher orders more easily and to some extent as you still have the problem with the CFL criterion, but it isn't, the scheme that's used in the Seisol is called ADER, and ADER stands for arbitrarily high order discontinuous Galerkin method. Okay, just a few more points. What I presented you is a nodal approach. A nodal approach means we use basis functions that that have these collocation points, but you can also use a modal approach, in which case this is something like if you want like splines, you do not have these collocation points, but you describe the function with another set of basis functions, and actually Seisol, in Seisol that is the case. You have more number of degrees of freedom in this. I mentioned this before. And another aspect, if you going back to if you think of a problem like this, where you have many different mesh sizes, element sizes, you may change the number of polynomial order in each element. Suddenly you get a big problem with the load balancing. Load balancing means that if you have a parallel computer, that all the different machine parts operate at the same time, and so that then is really an increased complexity on an implementation level. Okay, that's basically it. Let me finish here saying, well, all this indicates, and that's a graphic of Martin van Driel, who was a Tarja's student. The forward problem is solved, but there's still a lot of problems. In particular, things we haven't talked about is like the mesh generation. If you have a complicated geometry or want something involved, that's a big issue. And some methods work better with or are easier to be meshed. A major statement is that tetrahedral meshes are much easier generated than hexahedral meshes, but then tetrahedral algorithms are more expensive. So, there's a trade-off. So the forward problem is solved in quotation, but there still remain a lot of things to do. So let me stop here. So we've been half an hour now into this final leg, and ask you whether there are any questions at this point. Silence. So if not, I encourage you to, let me just open the exercises. I really encourage you now to play around, and I suggest, if you're willing to do that, that at least you spend like half an hour now with these questions, discuss them in the breakout sessions. Let me open the, so there's a couple of questions here. Just maybe just discuss those. And then I have suggestions here as what you can do with these. I suggest one spectral element code and one DG code, and just simply play around with the parameters. I hope they work. So you have access to the exercise sheet in the GitHub, and you know, use any of the three possibilities to work with these codes, either directly in the repository with MyBinder, on Seismology with MyBinder, or download these codes and run them locally. Okay, and so any questions, comments? Otherwise, I would start the breakout sessions.